Section 14.4, the chain rule. So a couple learning goals here: be able to apply the chain rule in many different situations and draw appropriate diagrams. Also be able to perform implicit differentiation using the chain rule. Okay, let's just start off with an example to get things going. So suppose that f of xyz is equal to xy, x times y plus z. But further suppose that x, y, and z are all actually functions of s and t in some way. So x is s squared, y is s times t, z is t squared. So really, f is x, y, z, but x is a function of s and t, y is a function of s and t, z is a function of s and t, is really a function of s and t. And so if this is really a function of s and t, a very natural question for us to ask is, how does f depend on s and t? Or in other words, what are we going for? We're going for df ds and df dt, the partial derivatives of f with respect to s and t. Okay, so one way to do this, the brute force attempt at this would be to replace x, y, and z with their respective things. So f is going to equal x, which is s squared, times y, which is s times t, plus z is t squared. And so if we want to calculate, for example, the partial derivative of f with respect to s, we can read this off, so that would be s cubed times t would give us 3s squared t, and the partial derivative of this with respect to s would be 0. And df dt would be, let's see here, the partial derivative of this term would be s cubed plus 2t. Okay, so this is the brute force attempt, and this is not too difficult. This is not too difficult to do, but, I chose a relatively simple function f here in terms of x, y, z. I chose relatively simple, function x, y, z in terms of s and t. So the question that we should ask is, could we have done this? Without expanding. And just to kind of motivate this, to go back to one variable calculus in the chain rule, if your function g of x is equal to, let's say, x cubed plus 1 squared, and you want to take the derivative of this, you could use the chain rule and say the inside function is x cubed plus 1, the outside function is x squared here, or you could just, multiply this out and get x to the 6 plus 2x cubed plus 1 and take the derivative of this. So either way, chain rule or no chain rule is about a wash, but if your function was actually x cubed plus 1 to the 100th power, trust me, you do not want to expand this out and then take the derivative. The chain rule would be far, 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 far simpler. So we're looking for an alternative way to do it that would work in more complicated situations. And so given our original function f in terms of x, y, and z, and x and y and z in terms of s and t, I made a little chart here. And so what I did was I wrote down, okay, so this first row here is the partial derivatives of f with respect to x and y and z. So like the partial derivative of f with respect to x is, so the partial derivative of this would just be y, with partial derivative with respect to x, so on and so forth. And then Down here I have the partial derivatives of x and y and z with respect to s and t. And so, for example, the partial derivative of x with respect to s would be 2 times s, but there's no t dependence, so that partial derivative there is 0. Okay, so there's one more little change I want to make here, which is our final answer here was written completely in terms of s and t. And so I want to rewrite this first row in terms of s and t. So y is actually s times t, and x is really s squared. So the question is there a way, using the pieces that we have here, using the pieces on this piece of paper, is there a clever way, is there a nice pattern to be able to come up with the partial derivative f with respect to s? And as it turns out, there is. What we can do, so we're looking for 3s squared t. If we do this times this, 2s times st will give us 2s squared t, plus this times this would give us a third s squared t, plus this times this would give us 0. And so what is going on here? The partial derivative with respect to s is equal to the partial derivative with respect to x times the partial derivative with respect to x, partial derivative of x with respect to s, plus the partial derivative of f with respect to y, times the partial derivative of y with respect to s. And then, for symmetry's sake, we need to throw in partial derivative f with respect to z times the partial derivative of z with respect to s. And so what is going on here, so once again, the pieces are, this is s times t times 2s plus df dy is s squared times t plus 1 times 0. And sure enough, that gives us 3s squared t as appropriate, as desired right here. So let's just take a moment to look at this formula right down here. You know, how to know this formula. The partial derivative of f with respect to s is you take all possible intermediate variables. You could have x as an intermediate variable, y as an intermediate, z as an intermediate variable. Form the products of df, partial f partial x times partial x partial s. Multiply that together, plus partial f partial y times partial y partial s. Multiply those together, multiply these together, and add up all of those terms. Let's also see, similarly, the partial derivative of f with respect to t now is going to equal the partial derivative of f with respect to x times the partial derivative x with respect to t, plus the partial derivative of f with respect to y times the partial derivative of y with respect to t, plus the partial derivative of partial derivative f with respect to z times the partial derivative of z with respect to t. And if we multiply everything here together, so this would be st times 0 plus s squared times s plus 1 times 2t, and putting all of this together, 0 plus s cubed plus 2t, once again, is the same answer as we had before. So this is our first illustration of the chain rule, and for multiple variables here, we'll definitely have a lot more examples coming up, but this should give you some idea for what's coming up.